Welcome to Study Loop.
This is the answer to Chapter 12, problem number 65 from the Smith Organic Chemistry textbook. And in this problem, we are asked to synthesize 4 molecules, starting from acetylene and using any other reagents that we need. Starting from acetylene, acetylene is a 2-carbon molecule. Each of these is a 4-carbon molecule. So the very first thing that we're going to need to do is going to be to add 2 carbons. These are also all epoxides or diols. So the way that I envision doing this is deprotonating this acetylene. And so we can then treat the deprotonated acetylene with methyl chloride. That's going to add 1 carbon. And then we can just repeat that step to add a carbon to the other side. Okay, and so now we have a 4 carbon chain, and so that's going to be a good starting point for all of the molecules that we have to make here. And so specifically to make A, the next thing that we would want to do would be to treat this with some hydrogen gas and Lindlar's catalyst. And that's going to give us the cis alkene. Okay, and so from the cis alkene, if we treat that with MCPBA, that's going to get us the epoxide that we are asked to make for part A here. Okay, so there's A. Fortunately, we can use intermediates that we made in A for all the rest of these. So for B, we can start from that 4-carbon alkyne that we made in A. So we can start from here. And then we're actually going to do exactly the same thing, but this time we're going to do a dissolving metal reduction instead of the Lindlar's catalyst reduction. So the utility of the dissolving metal reduction is that it's going to get us the trans version of this alkene. So for A, we needed the cis version. For B here, we want the trans version. And then again, when we treat that with MCPBA, we will get an epoxide. But this time, we'll get this epoxide. And it's enantiomer. And that is what we are asked to make for B. All right. So then on page 2 here, for C, we want to get to a diol. And so we can start from here. So we'll start from the alkene that we made in A. So this cis alkene, and then we can treat that with potassium permanganate. So KMnO4, water, and some base. And that's going to get us to here. Too high up, I'm afraid. So that's going to get us to here. There we go. All right. And then, so that's our product for C. And so for D, just like we did going from A to B, we're going to do the same thing going from C to D here. So whereas we used the cis alkene that we made in A to get our product for C, for D, we can just use the trans alkene that we made in B and treat it with potassium permanganate again, just as we did for C. And that's going to give us our product this time. So this is from B. Everything else was from A. That's fine. So as I said, potassium permanganate once again, water, base, and that's going to get us to. That's going to get us to here. And it's an enantiomer. Okay, and so that's D, and that's the answer to this problem. So really, to get started, we just need to remember how to make carbon-carbon bonds, starting from an alkyne, and so we deprotonate it and react it with methyl chloride, and then do that a second time. Then we have our 4-carbon chain with the alkyne in the middle, and then from there it's just a matter of picking the right reduction for the intermediate that we want, whether that's cis or trans. And then once we've picked the right reduction, using MCPBA, which I forgot to write here, using MCPBA to epoxidize it, or using potassium permanganate to get to the diol instead. And that's the answer to chapter 12, problem number 65.